Okay, so continuing with substitution, now let's do a definite integral, right? So this is a definite integral from 2 to 4 of the cube root of 5x minus 2. Oh, I forgot the dx. Let's make sure you have dx there, right? So that's the problem we have here, right? And it turns out there's a couple ways of doing this, but I'm going to do it sort of the most direct way possible here. Well, first thing we should do, of course, is rewrite it with an exponent. So this is 5x minus 2, right, to the power 1/3, right, because it's the cube root now. So now we have an exponent of 1/3. And as before, we can't just do, x to the 1/3 because you're taking the cube root of 5x minus 2. So that, inside the parentheses, that should probably be what I'm going to call u here. And so the derivative of 5x minus 2 is just 5, right? So you can see I'm missing a 5 with the dx. So no problem, just multiply by 5, as long as you also divide by 5 on the outside. Oops, that should be a 5, yeah. Right, and so this becomes my du. This becomes u to the 1/3, right? So now we can write the problem as 1 over 5 times the integral of u to the 1/3 du. Right? And now we can just use the power rule for antiderivatives, right? We just do 1/3 plus 1, right, which is 4 over 3. Before I do that, though, you might notice, well, isn't something missing, right? Remember, this was a definite integral. We had the lower and upper limits of integration. And so you might think, well, yeah, I'm missing the 2 and the 4 here. Well, yes, we're missing numbers here, but it's not 2 and 4. Yep, these are wrong. Right? You can't just do that. So why not? What's wrong with that? Well, keep in mind what the 2 and the 4 represented here, right? These were values of x, right? We're going from x equals 2 to x equals 4, right? In the original problem, this was all with respect to x, so the upper and lower limit are, of course, values of x. And maybe I won't ruin the original problem. I'll just write the x's over here, that these were x equals 2 and x equals 4. So if you write 2 and 4, these are x's, but we're integrating with respect to u, not x. So we can't do that, right? So here's one way to do the problem, is to change the limits. Instead of 2 and 4, what are they going to be? Well, remember what u is. U is 5x minus 4. So what if x is 2? Right? So what's u going to be? It's going to be 5 times 2 minus 2, right? 10 minus 2 is 8. So instead of 2 here, we're going to change it to u equals 8, because that's saying x equals 2 is the same as saying u equals 8, right? If x is 2, u is 8. Right? Now what about the upper limit here? What's u going to be here? Well, let's calculate that. If x is 4, right, then u is going to be 5 times 4 minus 2. That's going to be 20 minus 2, which is 18. So here u is going to be 18. Okay. Right. Now we can integrate, right, as we ordinarily would. So we find an antiderivative, an indefinite integral of u to the 1/3. Again, don't forget the 1/5. Right. So when you add 1/3 plus 1 is 4/3. I think I mentioned that already. U to the 4/3. And then divide by 4/3 plus c. Oh, we don't need the plus c here, right? Because remember, we're going to use the fundamental theorem of calculus. We're going to plug in 8 and 18 in for u here. Before we do that, though, let's multiply by 3 over 4. So 3 over 4 times 5 is 3 over 20. And then this is going to be u to the power 4/3. And now we can plug in the 8 and the 18. Right? So this will be 3 over 20 times 18 to the 4/3, right, minus 3 over 20 times 8. I'll put that in parentheses, 8 to the 4/3. Yeah. Okay. Now, what's 18 to the 4/3? Well, 18 is 2 times 9, and 9 is 3 times 3. There's no perfect cube, so it turns out that's probably as simple as it gets. The only thing you could do is write it as, 18 times the cube root of 18. I don't know if you want to do that, but okay, I guess we'll do it that way. Minus 3 over 20, and we could have factored out the 3 over 20. In other words, we could have done it this way. I decided to distribute, so that's supposed to be 20. So this is the cube root of 8, which is 2, and 2 to the 4th is 16. So that works out to a nice number. Obviously, this one does not. Okay, so what do we have? Well, 18 over 20 is just 9 over 10. So I think this is 27 over 10 times the cube root of 18. And then minus, let's see, this is going to be 4 over 5. So 3 times 4 is 12, 12 over 5. And I don't see anything else we would really want to do there. So this is the exact answer. You can plug it in a calculator and get an approximate answer, but this is good enough. Remember, this was a definite integral, so the answer is going to be a number here, right? And in this case, the number was, I forget, 27 over 10, or 2.7, right, times the cube root of 18, and then minus 2.4, right, 12 over 5. I'll leave it that way. So remember what that number represents. It represents the area under the curve. Right. In this case, the curve is y equals the cube root of 5x minus 2. So you graph that curve, and you calculate the area, right, between x equals 2 and x equals 4. Yep. So that's what you could do when you have a definite integral. The other option, instead of calculating what we did here, calculating the new limits in terms of u, right? Remember, we had to change our x's here into u's over here because we changed these x's in the integrand. We changed them to u's here as well, right? So we have to be consistent. Change all the x's to u's, including the limits, the upper and lower limits of the integral, right? Yeah, so that's one thing. The other thing you could do is, after you calculate the indefinite integral in terms of u, you could, of course, go back to x, right? So we could, and I'll have to do this down here, right? Write this in terms of x. So this is still going to be 3 over 20 times, 5x minus 2 to the 4/3, right? And now, instead of plugging in the 8 and the 18, as we did here, we plug in the original x's, right? The original x's were 2 and 4. Oops, sorry. So now we're plugging in x equals 2 and x equals 4. Right? So what happens when you do that? Well, you'll still get 3 over 20, and, well, I didn't factor out here, so I'm not going to factor out here, right? So we get 5 times 4 minus 2 to the 4/3 minus 3 over 20 times 5 minus 2. I'm sorry, 5 times 2 minus 2, also to the 4/3, right? Of course, when you calculate out all this, 20 minus 2 is 18. Oops, 4/3 minus 3 over 20 again times 10 minus 2 is 8. And, of course, you get the same thing that we did way up here, right? So it's just a matter of your preference, right? What we did here is we calculated the x's in terms of u. We did that already up here, so we didn't have to do it again down here. So either way is fine, right? Either way is fine. I prefer to change the limits, but I'm not going to ask you to do it one way or the other, of course. It's up to you. It's good to know both ways, and it's good to change the limits in most cases because, in this problem here, we didn't have to go back to x. We could have left it as u and just calculated these numbers in terms of the u's rather than the x's. But when you're doing an indefinite integral, you have to go back to x anyway, right? We would have to write it this way in terms of x, right? And you'd have a plus c here if it was indefinite. So that way makes sense too, right? But you get the same answer either way, right? And I didn't finish working this out here, but because it's the same thing, you're going to get the same answer here. Okay, so enough spaghetti here. Let's do another one of these definite integrals. Okay, so here's another one. We want to evaluate the definite integral from 1 to 4 of this fraction here. The numerator will be 3 plus square root of x, all to the 4th power, and then the denominator will be square root of x. So again, it's a quotient, but we're doing integrals, not derivatives. There's no quotient rule here. So what do we do? Well, again, we see parentheses. That usually calls for u. So u, let's make sure that's what's in the parentheses. The 3 plus square root of x. Right? So what's the derivative of that? And usually I just go directly to du, but let's write it as the derivative of u with respect to x, right? So the derivative of 3 is 0. Remember what the derivative of the square root of x is? Well, if you don't, change it to x to the 1/2. So you just get 1/2 x to the negative 1/2. Well, dx if you multiply both sides by dx. So that's my du. Right? And you might say, well, but I don't have an x to the negative 1/2. Well, sure you do. It's 1 over the square root of x, right? So it might be helpful to write this du as actually 1 over 2 times the square root of x, right, dx. So because that's what we have in the original problem, right? We have 1 over, well, we don't have a 2 here, so okay. We're dividing by 2, so on the outside we'll have to multiply by 2, just the opposite of dividing by 2, right? But actually, let me keep the original problem intact. Let me just copy this down. And we'll do the same thing out here. Right. So same numerator, same denominator, all with respect to x. So, yep, in order to make this into a du, here's my du. The only thing I'm missing here is this extra 2, which I don't have over here, right? So, yep, so we'll just multiply the denominator by 2 on the inside. That means we multiply by 2 on the outside, right? And effectively that would cancel these 2's, but we don't want to cancel them, right? So we have our du, and if it's not clear, maybe we should write it this way. How about if I write this as 3 plus the square root of x, all to the 4th power, and then just move this under the dx here. This is dx divided by 2 square root of x, right? You can do that, right? You can just slide the denominator back and forth. After all, you're just multiplying, right? Okay, makes sense? I hope you can do that, right? Yeah, so that, of course, is my du. It's just dx, that's an x, divided by 2 square root of x, right? So let me just make that clear, that all of this now becomes du, and all of this, right, becomes u to the 4th. So we still have the 2 on the outside. That doesn't go anywhere. So this is u to the 4th du. Well, I don't need that much space here. So yeah, u to the 4th du. So that comes over here. But remember, you don't copy down the limits. This is not 1 and 4 anymore. Don't make that mistake, because if you do, you're just going to get the wrong answer. Okay? So yeah, remember, at this stage here, this was all still in terms of x. So these are x's. X is 1 and x is 4. So what's u going to be? Oops, it's not 1, right? I don't think it's going to be 1. So we have to figure out what u is in terms of x, right? Again, the other option is to not do that. Leave these off, right? Don't even write these. Do the indefinite integral, change back to x, and then plug in x equals 1 and 4. Okay. But like I say, I tend to change the limits here. So let's figure out what these limits are, right? So what was u? Here was u. 3 plus the square root of x. So if x is 1, let's do the lower limit first. We're doing x equals 1 first. Then what's u going to be? Well, it's going to be 3 plus the square root of 1, which is 3 plus 1, which is 4. Oops, sorry, 4, right? So my u should be 4. And if x is 4, I'm running out of space here, so suppose now x is equal to 4, then what's u going to be? It's going to be 3 plus the square root of x, but x is 4, so 3 plus the square root of 4 is 3 plus 2, which is 5. So my lower limit is 4, my upper limit is 5. Right. So now we can do this integral. Again, 2 over 1 is just 2 times the definite integral from 4 to 5 of u to the 4th du. So all multiplied by 2, right? So now we can finally do this integral using the power rule. This is just going to be, well, u to the 5, right? U to the 5 divided by 5 plus c, except there's no c here. We just plug in the 4 and the 5. Right? So we're going to get 2/5 times u to the 5, and then we plug in the 5 first and then the 4. Oh, I can do that here, right? So this is going to be 2 over 5 times 5 to the 5 minus 2 over 5 times, sorry, that's a 5, times 4 to the 5, right? Which are some pretty big numbers here, right? So 5 to the 5, I want to say 3125. I know it's 625 times 5. Yep, 3125. But then you're dividing by 5. So this is really just going to be 2 times 625. Oops. And then, unfortunately, this is not going to be divisible by 5, right? So what's 4 to the 5? I think it's 1024. And in fact, 2 times 1024 is 2048, all over 5. Yep, so I guess we're going to get 1250 minus 2048 over 5, which is some number. Maybe let's get a common denominator, right? So 1250 times, oops, sorry, hang on. Okay, I think I got it. I think it's 6250 divided by 5 minus 2048 over 5. And when you subtract the numerators, yep, you get 4202 divided by 5. Or, if you prefer decimals, 840.4. Oh, sorry about that. 840.4, right? Either way. So that's the answer here. So this is, yep, this is equal to 840.4. Right, and that's the area under this curve here, y equals whatever this is, right? So that's, yeah, that's how you do definite integrals using substitution. Again, you didn't have to do it this way. You could have, right, at this stage here, right, instead of plugging in the 5 and the 4, you can say that this is 2 over 5 times 3 plus the square root of x to the 5th power. And then this you would evaluate at the original limits, which I think was 1 and 4. Yep, 1 and 4. And if you do that, of course, you just end up with the same thing as we did down here. Oops, not quite that. Yep. You end up with the same number. Okay? All right, so that's definite integrals with substitution. Okay, so I think we have to move on. There's a property in this section that I almost think doesn't belong there. Oh, I'm out of space. So let me clear this, and then we'll get to the property. Okay, so there's one theorem, one property in this section, and it goes like this, right? So we're assuming that f is an integrable function on this closed interval from negative a to a, right? So you're just going from the negative number to the positive number, right? So here's my interval, right? Here's 0. We're going from minus a on the left to plus a on the right. So again, think of that as my x-axis. If we have an even function, right? So if f is an even function, and I hope you remember what that means. If not, let me remind you, f is even if f of negative x is the same as f of x for all x in the domain. I'm sorry, I'm writing small here. Feel like I'm going to run out of space, right? So that's what an even function is. Then, if you want to calculate the definite integral from minus a to a, you could do that directly, or you can just go from 0 to a, right? This is a 0 here. You can go from 0 to a and just double the definite integral. Okay. Now, why does that make sense? So let's look at a typical, pretend that's the y-axis, a typical even function. So a typical even function might look like this. Right. So then this would have to go up like that. I missed a little bit. You know what? Let me just make this a little more obvious. How about if this is like x squared? Something like that. That's a typical even function, right? Right. So notice that we want the area between negative a and positive a, right? So it's going to be all of this area in here, right? As well as this area in here. And you can see I'm a little bit sloppy here. This should be a little more like this. Should look the same on both sides, right? It's symmetric. It's symmetric with respect to the y-axis, right? This is the mirror image, right, of the other side, right? But that's the key, right? Because if I'm going from 0 to a, right, just this piece of it here, well, that's the same area as it is over here. It's just a mirror image, right? It's the same area. So you might as well just go from 0 to a and just double it, right? Double this area here. If I take 2 times this area, I get this area plus this area because, well, 1 plus 1 is 2, right? You get the same thing. Right? So hopefully that you understand where that 2 comes from. You're just doubling the area from 0 to a instead of going from negative a to positive a. Okay. All right. The second part to this is what happens if you have an odd function. So remember what an odd function is. I'll remind you, f is odd. Oops, odd. If f of negative x is equal to negative f of x, right, for all x in the domain. Same thing for all x in the domain. And if you have an odd function, right, again, it has to be odd. It doesn't work for all functions. It only works for odd functions. If you're going from negative a to a, well, it doesn't matter what the function is. As long as it's odd, you get 0 here. Why does that make sense? Well, let's draw the picture here. Yep, so let's draw an odd function. So what would be an odd function? Something like x cubed, right? So you might have a function that looks like this. Again, we'll call that this is a here, and this is minus a. So now, okay, close enough, right? So we're going from minus a to positive a here, right? So we want to calculate the total area from negative a to a, so that's going to include all of this, right? As well as all of this down here. Right. Now, why am I drawing this in red? Well, remember, this is below the y-axis, and below the y-axis, the definite integral counts this as negative, right? Whereas over here, this is above the x-axis, the definite integral counts this as a positive, right? So otherwise, it's the same area, right? But you're taking a pot. Let's say this area is, oh, sorry, I should use red here. Let's say that this area is, 17, right? Then this area over here will also be 17. But the definite integral from negative a to 0 of whatever this function is, right, will be negative 17 because it's, again, below the y-axis. The height of the rectangle would be negative, right? But if you're going from 0 to positive a of the same function, you get positive 17. So when you combine them, right, if you're going from negative a to 0, and then you're going from, dx, and then you're going from 0 to 0 to positive a, right, you just get negative 17 plus 17, which of course is, let me try that again. You just get 0, right? So that's why this equals 0 up here. Make sense? Oh, got erased again. So these are the two properties here. By far the most useful one is the second one here, right? This one here turns out to be very useful, allowing you to evaluate definite integrals of this form that you wouldn't ordinarily be able to do, okay? So this makes it a lot easier. This rule up here, I guess, is also useful in some cases. It does allow you to avoid having to do a lot of negative signs, because when you change the negative to just 0, you avoid negative signs there, right? So they're both helpful, but I think the second one is even more helpful. So I'll show you an example of that. Okay, so here's an example. We want to evaluate the definite integral from negative pi to positive pi of x cubed cosine x cubed times cosine of x dx. Okay, so how do we do this, right? So notice this is a product. This is a product here, so there's no product rule for integrals. So you might be tempted to do substitution, but there's no parentheses. So what would you substitute? X cubed, u is x cubed, then du would be 3x squared dx. And this does not look anything like this. There's no match whatsoever here, right? So that does not work. So what's your other option? U would be cosine of x, but then du would be negative sine of x dx. And that negative sine of x doesn't look anything like the other factor, right? X cubed is not negative sine x, so that doesn't work either, right? And so this is hopeless, right? It turns out that this integral up here cannot be done by substitution, right? So substitution just does not work. It was a good try, but it just did not work in this case. So how can we do this? Well, it turns out this is possible by a technique that you're not going to learn until Calculus 2. And yet, what is this doing in Calculus 1? Well, if you remember the rule up here, if we're going from negative a to positive a, now a being a being pi in this case, 3.14, right? You're just going from the negative to the positive, right? So the integral from minus a to positive a of any odd function is just 0. Now, before we can say that this equals 0, we don't know that yet. we have to check that this function in here, this is my f of x, right? Is this odd? Is it odd? Well, remember what an odd function is. I wrote it down up here. Yep. F of negative x equals negative f of x, right? So let's check that here. If I replace x with minus x, I have to do that here, and I have to do that here. Right? So negative x times negative x times negative x is negative x cubed. And cosine of negative x, you should know this. Cosine is an even function, so that's just cosine of x. Well, what is this? This is just negative f of x, right? So f of minus x equals negative f of x. That means the function is odd. So we can erase the question mark, right? We can say that this is odd. And if it's odd, well, by this rule here, right? Again, this is only true if f is odd. Luckily, it is. So the answer to the problem, without doing any complicated substitution or any weird technique that we don't know about yet, this is just equal to 0. Right? Now, why is that? Well, because we checked over here, because x cubed times cosine of x is an odd function. You have to say that, right? Because essentially there was no work to show here, right? That this is equal to 0 by this theorem, by this property here. So you have to say why it's 0. It's 0 because it's an odd function, right? Because this integrand here, yep, this thing here is an odd function. And why is it odd? Well, you should check that right here. You should do this calculation to really make sure that you know it's an odd function. Okay, so that's your work, right? You have to show, right? You have to say that it's an odd function, and you have to show that it is an odd function. Then I will believe you that you know that this is 0. Okay, so I hope that helps. Okay, so I know this was a long section, but let's just do one more example. And this is one for solving what's called a differential equation. A differential equation is just an equation involving the derivative. In this case, the derivative of y, right? So we know the derivative of y. This is given, right? This is given in the problem. We know the derivative of y. We have to find y itself, right? So we have to undo the derivative. Right? And how do you undo the derivative? Well, you do the integral, right? That's an antiderivative. So y is just going to be the integral of cosine of x divided by the square root of 1 plus sine of x, all with respect to x, right? Yep. So this is what's called a differential equation here on the left. But it's a pretty simple one in the sense that you can solve it just by doing an integral. That's not always the case. But that's all we can do here anyways. Right? So we have our answer. This integral, that's going to be y. But they want us to get this as a function. So we have to evaluate this indefinite integral here. Okay. So how do we do that? Well, of course, this is a quotient. It's a fraction, but there's no quotient rule. So it looks like we're going to be stuck doing substitution again. And, well, it may be, okay, so it may be helpful to rewrite this, this y here. Let's write it as, not the cosine first. Let's put 1 over the square root of 1 plus sine x. This is going to be, in parentheses, 1 plus sine x to the negative 1/2, right? Negative because it's in the denominator, and 1/2 because it's the square root, right? Times cosine of x dx, right? So I changed it from a quotient to a product. Again, no product rule, but this might make it easy to see what my substitution should be, right? So what should u be here? Again, rule of thumb, whatever's in the parentheses. Again, That doesn't always work, but I think it works pretty well here. So let's take the derivative of 1 plus sine x. So du is going to be 0 plus cosine of x dx. Right, so in other words, my du is just cosine of x dx. Right? And that's what this is here, right? So that's going to be my du. And all of this is going to be, well, u to the power negative 1/2. So, indefinite integral of u to the negative 1/2 du. So that worked out perfectly, right? We didn't have to multiply by any missing numbers here. We didn't have to multiply by 3 and divide by 3, you know. So, you know, we got lucky. Sometimes you don't have to do that. Yep, and now just use the power rule. And we did this one earlier, I think. This is just u to the positive 1/2. So 2u to the 1/2 plus c, right? Or better yet, 2 times the square root of u plus c. Of course, we can't leave it in terms of u. What was u? u was 1 plus sine x, right? So let's replace that. So my y here is really just, oops, sorry, not u, y. So y is equal to 2 times the square root of sine of x plus c, right? Plus c because it was an indefinite integral. There's no, right, there's no limits here, right? We're not going from 1 to 6, right? It's an indefinite integral, so you do need the c. However, in this problem, and you might remember this way back in from section 4.1. We did problems like this way back in section number 4.1, where we had a differential equation, and they gave us this piece of information, right? Remember, this is called an initial condition, right? Because what it's saying is that when x is 0, y is equal to 5. So let's plug that in here, right? When x is 0, y is equal to 5, right? Hang on. No, okay, so all right, what I just said is fine, but I'm missing something here. My u was not just sine x. It was 1 plus sine x. All right, so let me fix that. Yeah, so get rid of the sine x. This should be 1 plus sine of x. Sorry about that. No. You know, I've been doing this for a while, so I'm getting a little tired. Maybe that's, you know, that happens. Okay, so now go back to my original idea here. X is 0 and y is 5. So just plug in x equals 0, y equals 5. And here's what we get, right? We get 5 equals 2 times the square root of 1 plus the sine of 0 plus c. Well, sine of 0 is 0, right? 1 plus 0 is 1. So we just get 5 is equal to 2 times the square root of 1 plus c. But the square root of 1 is just 1. So you get 5 is equal to 2 plus c. So subtract 2 from both sides. C is going to be 3. So because of this initial condition way up here on the right, we know what c is. So now my y is just 2 plus the square root of 1 plus sine x. Sorry, I forgot the 1 there. And then remember, c is 3, so this is plus 3. So there is our final answer. Okay. And so that's what y is, right? So in other words, we know the derivative of y is this over here on the upper left. That's the derivative of y. Well, how do you find y? You do the opposite of taking the derivative. You do the integral. In this case, an indefinite integral. So we did that. We had to use substitution, of course. That made it a little complicated, but it was a typical substitution. And then we got y with our constant of integration. Then, because of the initial condition up here, this initial condition here, we were able to solve for c. And then once you know what c is, you just plug that in, and there's your answer without a c. Right? So now it's well, I don't want to say definite function, but it's a function. Y is a function of x. Okay, so I think that's enough. You should be able to do all the problems in, I think it's section 4.5, substitution. So I hope this helps. And if you have any questions on the homework, please feel free. I will get to your questions eventually. And if it's a question I can't answer by email, I'll just make another video out of it. So that should take care of 4.5, and that takes care of all of chapter 4, at least for now.